eta 0, where eta 0 is either 0 or 1 for each side x in Z, 1 representing a particle and 0 representing a whole. And at each side there is a clock, Poisson clock. When the clock rings, if there's a particle, it would like to move to the right, but it can only move if there's a hole to the right of it. It cannot jump onto another particle. That's why it's called an exclusion process. So there's a little reminder here on the blackboard of that idea. And so all the particles are moving to the right in this process. And we would like to introduce a second-class particle. It's a famous notion. And we do this following an idea of Leandro and Pablo Ferrari by introducing a whole particle pair. So what's the idea? We had the configuration eta 0 with all the particles in the holes. And now we keep everything to the left of 0, we keep the same. And everything to the right of 0, so starting at side 1, etc., we shift it to the right so that we get an extra side. Instead of only the side 0 in the middle, we now have two sides. And this left side will give a hole, and the right side will give a particle. And in that way we have a new configuration, eta 0 bar. And this 0, 1, that's called the whole particle pair. And we will keep an eye on that as the eta bar configuration evolves according to the Tarseb rule. So this whole particle pair, that will be what we call the location of the second class particle. So that's this xt here. No, it stops. Xt is the location of the whole particle pair, and it follows the following rule. If, suppose that this is the origin, so this whole particle is the actual pair we are looking at. Now, if the particle moves to the right, then we say that the whole particle pair also moves to the right. Because if this one jumps, a hole is created here, and we can say that the pair is moved to the right. Now, the other thing that could happen is that this particle would make a jump here, and then make another jump here onto the hole of the whole particle. Now, if that happens, if this particle jumps onto this hole, then we say that the whole particle pair actually moves to the left. Yeah, because if there's a particle here, jump to the hole, then we have here a new whole particle pair. So this whole particle pair, or the second class particle, can move to the right and it can move to the left. And we are interested in its behavior given certain initial configurations of the second class particle. And the kind of configuration we are looking at is called a rarefaction fan. And that basically means that if you look at the density of particles to the right of 0, that should be smaller than the density of particles to the left of 0. And in fact, the actual densities don't have to exist. That's why there's a lim sup and a lim inf, but you can think of it like that. So you have more particles to the left than to the right of 0. And then you get a rarefaction fan. And it turns out that in that case, oh, that's strange. Well, there's a mistake here. But, in that case, you can prove, and it was done by, in fact, this should be James Martin, Pablo Ferrari, and Pimentel in a 2009 paper, that this second-class particle, or the whole particle pair, the second-class particle will get some asymptotic speed, so it will follow some straight line after a while. However, the speed is random, and it always lies within what they call the rarefaction fan. So we know that this speed exists, but we don't know the distribution of this random speed. And in fact, there were only very specific initial configurations for which this distribution was known. And one example is if you take Bernoulli particles, Bernoulli random variables to the right of 0 and also to the left of 0, but with different intensities. So that's a very specific case. And in that case, you could prove that the speed was actually uniform. But like I said, it's more or less the only case. And so it was a long time unknown how to calculate this distribution. And Leandro and I managed to do that. For arbitrary initial configurations, we could have a formula for the distribution of the asymptotic speed of the second-class particle. Now, to give you this formula, I need some more notation. And This notation will also come back later when I discuss some ideas of the proof. So what happens is that we have a lot of exponential random variables with intensity rho or 1 minus rho, and all these exponential variables are independent of each other, and they will be used to construct two random walks. One on the positive side of to the right of 0, and one to the left of 0 on the negative side. So I define my zk's. They will be the steps of the random walk. And these steps, they depend on whether the configuration has a hole or whether it has a particle. And we don't look at the actual configuration, we look at the eta bar, which is the one with the whole particle configuration inside. So when there is a hole, the zk for positive k takes a step down with a certain distribution, and when there's a particle, it takes a step up with a little bit different distribution. So that's for positive k's. For negative k's, it's the other way around. That means that it actually takes a step up when there's a hole, and it takes a step down with a certain distribution when there's a particle. So now we have the two random walks, one for the positive side, this one, which just adds up all the zk's for positive k, and we have one for the negative side, which adds up the zk's for the negative k's. And these two random walks, they are independent, and they're just sums of exponential, and which exponential depends on the configuration that you start with, the eta. Now, how can these random walks be used to describe the distribution of the asymptotic speed? That's in this theorem. If you look at the intensities, the particle intensities to the left of 0 and to the right of 0, then you can show that the speed, the random speed, is always in between these two values. So we will end up with a random variable with this support. We define rho of u to be equal to 1 plus u over 2. That's the same rho we saw in the previous slide. And then when you have a rarefaction fan, we know that you get almost sure convergence to some random speed, and the probability that this random speed is bigger than little u, well, that's exactly the probability that the negative random walk, the random walk on the negative side, has a bigger maximum than the random walk on the positive side. And these two random walks were independent, they made up and down steps, and for the choices of rho that we are interested in, so that's the rho such that the u is inside this support, we will always have that both random walks have a negative drift, so in the end they will go to minus infinity, and for these suprema they are both finite, and we're interested in the probability that one of them is bigger than the other one. And if you can calculate that, then you would have the asymptotic speed of the second class particle. Now that looks, kind of complicated, and maybe it's just as complicated as the original problem, but that's not true. So I will give you an example of where we can explicitly calculate the distribution of this random speed. We take a more or less periodic configuration. That means that we start to the right of 0, we take k plus number of holes, then we have one particle, then we have k plus number of holes, then one particle, etc. And to the left, we do something similar, but kind of vice versa. So we take k minus 1 particles to the left, then one hole, then k minus 1 particles, then one hole, etc. So it's somehow periodic configuration, and you can easily see that since there are a lot of particles to the left, there will be more particles to the left than particles to the right. So we will always have a rarefaction fan as long as we choose one of the two bigger than 1. And so this will be a rarefaction fan, and you can have an exact formula for the distribution of the random speed, and it goes as follows. We define a lambda plus and a lambda minus. They are solutions of zeros of generating functions of certain variables. This has to do, these formulas, they come up with queuing theory, because these random walks, they form a sort of queue, and you can actually exactly calculate the distribution of the maximum, and therefore calculate my probability that I was looking for. So you get these polynomials. These are whoa, that's not so good. I have to cancel that. So these lambdas, they're actually solutions of polynomials. Yes? No? No. Oh dear. What did I do? I heard someone say yes, but maybe this is good enough. No, it's not. Good Lord. Yeah, will it stop now? I think so. So these are just polynomial equations. You can solve the lambda minus and lambda plus, and you get this kind of complicated formula for the distribution. But this is exact. There's no numerics or anything. You can just exactly calculate it. And the nice part is, if you look at this picture, what you see here, the blue line, that's the probability distribution that we have just calculated. And what is the red line? Well, let's say k plus is 2, so we have 2 holes, 1 particle, 2 holes, 1 particle to the right. So that means that you have a particle density of 1/3. And to the left, we take k minus equal to 1. So that means to the left, you have a particle density of 1/2. So you have 1/2 and 1/3. And if you would do Bernoulli's with 1/2 and 1/3, you would get a uniform distribution with a red line. But this is not Bernoulli, this is somehow more regular because it's this periodic thing. And what you can see is that it's very, very close to the outcome of the Bernoulli, but it's slightly different. So that's kind of cute that they're close together, but a little bit different. Okay, well, I don't have that much time, but let me just flip through the idea of the proof. The idea is to make the connection between TASEP and the last passage percolation on Z2. So we have Z2, on each of the lattice sides we take an exponential 1, what the hell? Random variable. Well, like I said, I will flip through it. The idea is that in this last passage percolation, you can, instead of looking at the initial configuration A to 0 for the original TASEP, in the last passage percolation, you can make an initial profile. And this profile that looks like this. It starts in 0, 0, it goes down and to the left always, and then it moves a bit like this and a bit like this. And you're looking at longest path from a point in the lattice to this profile. And for each of these points, so that's here, for each of these points you can look at whether the longest path is to the left of 0 or whether it's to the right of 0. And in fact you can make what they call a competition interface. So that's like this path over here. For all the points above the interface, the maximum is here to the left. And for all the points below, the maximum is to the right of 0. And this competition interface is directly linked to the second class particle. So the asymptotic angle of the competition interface, there's a direct link to the asymptotic speed of the second class particle. Now I won't go into this link, I'm just going to tell you how we can control this asymptotic angle, because that's the interesting part of the idea. So, what does it mean that the angle of this thing is bigger than some alpha? Well, let's say I take a line with angle alpha, and I say that my asymptotic, my competition interface is above alpha from some point on. What does that mean? It means that this point is closer to this part of the path than to that part of the path. So somehow we want to compare these distances, the distances to this, to the distances to this part of the path. And if we can compare that, then we will be able to calculate the probability and we'll be finished. Now, how do we do that? We do it as follows. So we want to, we fix now, so we want to see whether the distance to the positive part is bigger than the distance to the negative part. And I just subtract, from all these two things, I subtract this distance, the distance from 0 all the way to this point. So instead of looking at this distance, I now subtract this distance. And you can somehow feel that the difference here between these two distances, that might stabilize. And if it does, well, maybe we can say something about that. So that's exactly what happens. You can show that for every fixed k, if you have some point in the profile, sigma k, then the distance up to this x alpha point that's far away, minus the distance from 0 to that x alpha point, that converges almost surely, in fact for all k, to what we call the Buseman function. This Buseman function that depends on the angle alpha and, well, to the specific last passage percolation that we're looking for. So this thing stabilizes, and furthermore, we know a lot about this Buseman function. And we know, for example, that it's additive for all x, y, and z. And what's more important is that if you look at the Buseman function going from one part of the profile, so this is a part of the profile, and to the next part of the profile, so that's a step down in this case. So that's what it says here. If you look at the Buseman function from one part of the profile to the next point of the profile, let's call that a zk. And it turns out that we can prove that those zk's are either minus an exponential when there is a hole or plus an exponential when there is a particle. And of course, these zk's, they should remind you of the random walk that we saw earlier. So these zk's, they will form random walks, and then you can see whether the random walk in the positive side has a bigger maximum than the random walk on the negative side, and that's how you prove the whole story. Okay, I should stop here. Thank you very much.
Grosskinsky from Warwick University, and he'll be talking on metastability in zero-range condensation.
Okay, thank you very much. So thanks to organizers for giving me the opportunity to talk here. So yes, so I'm going to talk about recent results in collaboration with Ines Amendaris, Michalis Soulakis, and Paul Kleban. This is where I prepared the slides for the talk. It's just, and so what is a zero-range process? Let me start with this. So for simplicity, let's just see it's another stochastic particle system. It's somewhat similar to the TASEP, but with a difference here. In the zero-range process, you can have more than one particle per side. In fact, the number is not restricted. So we take a one-dimensional lattice for simplicity, put particles on the lattice, then with a certain rate, g, which is now a function of the number of particles on that side, one particle will move, say to the right with probability p, but to the left with 1 minus p. That's a model. You can also generalize this to all kinds of lattices, but let's not think about this here now. So the generator you can write down for this will look like that in a sense. Okay. Good. So this is the model here. So what are generic choices for this g? This is now a kind of this function as a parameter in the model. If you take g of k to be k, then you can think of that each of the k particles at the given side will move with rate 1. So these are in fact independent particles, and it's a very, very simple example of this model. You can also take g of k to be independent of the number of particles and think of these things as server queues. Okay. So these are two very simple examples, but the things we want to look at here now is basically where this g is a decreasing function in the number of particles, which induces an effective attraction between the particles. So that's what you can think of. And so a generic class of this thing is, okay, so here's called g of n. This is that this thing decays like b over n to the gamma. These are two parameters here, so it's a polynomial decay to some constant, which we can just set equal to 1. So this class has been introduced in 2000, and it has been studied a lot since then. And this is a generic example that will give you a phenomenon that is called condensation. There's also other things how you can get condensation, namely by having some spatial inhomogeneities, but I'm not going to talk about that here. So we will look at such examples. Okay. So what is condensation? So here we have just a snapshot from a simulation. So you start out with a homogeneous distribution of particles. That's particle number against lattice side. Let it run. And you see that when your density is high enough and your parameters are chosen well, then you will see a phenomenon that these particles tend to cluster in higher and higher clusters. These clusters will compete for particles. And in the end, if you run this for a very long time, you will have one huge cluster and fluctuating background here that you don't really see for the scale. So this is what happens in time. So the time evolution of this phenomenon is actually very hard to study mathematically, but there are quite a number of results in the stationary regime here, which I'm going to talk about. So we're only looking at the stationary case of this phenomenon. So the stationary measures of this process are very easy. So they're in fact product measures. So you can easily check that when you define your weight, so this W, this is for a single site now, basically proportional to the probability of seeing eta x particles here. This is just given by the inverse product of the jump rates. So if you plug this into your stationarity condition, you can check that it is fulfilled. So this is a simple computation. And now, of course, this is not necessarily a probability measure. You have to normalize this. There's two ways. Basically, Marek Biskup was talking about something very similar. There's a canonical way of normalizing it or a grand canonical one. Canonically, you just fix the number of particles in the system because the number of particles is conserved under the dynamics. So you take a lattice of size L, you throw in particles on it, you run it. You will see this pi ln will be the unique stationary distribution of this process. Okay, and so that's one way to write it. Okay, so this set ln is in fact it's a finite normalization. You can always compute it. So the grand canonical way of doing this is you don't fix the number of particles, so it's a random variable, but what you fix is the average number of particles by introducing a fugacity parameter phi. And you multiply your weights with this phi to the eta x. So you see that this will actually retain the product structure of the measure, so it's a bit easier to handle here. But the point now is that this normalization here is an infinite sum, because we are dealing with a particle system that has no bound on the number of particles per side. So this does not exist for every phi. You have to. So this will have a radius of convergence here. Let's call it phi c, and then these measures are only defined for phi smaller or equal than phi or smaller than phi c in the beginning, right? Okay, good. So and now also again very similar to what Marek was talking about in terms of this Bose-Einstein condensation. Something happens here. In fact, this phi c is now the radius of convergence of this partition function. Now what I'm plotting here is the expected number of particles under this product measure as a function of phi. In fact, I plot the inverse for some reason, because yeah, I'll explain that later. So this is now this is the inverse of the function, the density as a function of phi, right? And it exists up to phi c. So and the funny thing is that this could go like this. So you would have for every density you would have a measure, but in the typical case where you have condensation, this does not. So there is a largest density that you can have for these product measures. It's called the critical density rho c. Okay, and so why am I plotting it like this? Because this phi, fugacity, is not only a parameter here, but it turns out for this arranged process has a particular meaning. It's actually, if you have an asymmetric process, it's proportional to the current. So and what people like to plot for this process are these fundamental diagrams as current against density, right? If you have a symmetric process, it's kind of proportional to the diffusivity. Good. So and so on this blue part of the curve, I mean, whenever you have a density like this, you will see typically a fluid configuration here, which looks like it's homogeneous and you have a density rho. And of course, when we come back to this system, you can of course always throw in as many particles in your system as you like and let it thermalize, right? So and then the question is what will be the stationary distribution when I put in more than rho c particles on average? You can do that. And then you are on this part of the curve, and it tells you that a typical configuration here you will have a density rho c background, so you see density rho c, and then you have all the rest of the particles that you put in extra will be in one big cluster. Okay, good. So this is, and how can you see that? So this has been shown in so basically a series of papers that deal with this equivalence of ensembles question. So this is the canonical distributions, and they will typically want to converge to the grand canonical distribution in a thermodynamic limit, where the ratio of the number of particles over the lattice size tends to a certain value rho. This is the density, and then you have to choose this fugacity parameter correct, in a way that the expected density under the grand canonical measure matches this ratio rho that you're prescribing. Okay. You can do that as long as rho is smaller than rho c, but if it's larger, you cannot do that because these measures don't exist. But then, of course, what I've shown you here, this picture already suggests that in a certain sense, in a local sense at least, these canonical measures will still converge to a product measure with density rho c. That's what's written here, basically, right? So you choose the critical current here. Okay, so this, and then the question is, in what sense does this convergence hold? I mean, so that's not so important here, actually. So I've already written it in a weak sense. So you have test functions, so expected values of test functions will converge. Clearly, locally, this is rather straightforward to see in a very general context that you will have, for cylinder test functions that depend only on a finite volume, you will have a result like this. And what is a bit more involved is a more recent result by Ines Armendáriz and Michalis Soulakis, where they show that this also holds for global functions if you take away the maximum. Okay, so this is really a much more stronger result than, and this in the supercritical case, right? Okay, good. So this implies, in particular, that this is the number of particles in the maximum occupation number. That the maximum will cover a non-zero fraction of all the particles, and this is exactly this rho minus rho c and the rest. Okay, good. So, and you can summarize these results in phase diagrams, of course. So let me just come back to this particular example of functions, processes that I talked about before. So if you have these parameters for your g of n, turns out then when you fix here b over n and then b is larger than 2, you will have a condensed phase here, and here you will be fluid. So this is, you can compute these things then explicitly, and also for different values of gamma. Okay. So now the question. So these are kind of old results. Now new results. What happens on the critical line here, or say at criticality of this phase transition? In a sense, so the question is how does this cluster emerge when you put in more and more particles? So you take the thermodynamic limit again at the critical point. So n over L is chosen such that it converges exactly to the critical density. But then we have a bit of excess mass. So we put in n a bit larger than rho c times L, but sublinear in L. Okay. And then we want to investigate on what scale does this maximum show up and carry a non-zero fraction of the mass. So the question is the maximum. This is a maximum occupation number divided by this excess mass. What is this ratio converging to? And the answer is given in this picture, basically. So that's, say, a law of large numbers for this ratio. So you see, for example, let's look at gamma equals 1. So this is now a specific result for these particular jump rates. So this tells you that this ratio is always, it's either 0 or 1. And there is a critical scale, delta L, that you can identify explicitly. I didn't write it because it's a bit longish. And so this is known explicitly, such that when you are below this scale, so when this ratio tends to something smaller than 1, everything will be distributed homogeneously. And if this ratio tends to something larger than 1, the whole excess mass will be in a single side, and the rest is okay. And you see there's a certain jump here at this critical scale, right? So it's not really continuous. And the same, very similar thing happens when you have a gamma between 0 and 1 here. It's just a bit different that you don't actually, the condensate will not eat the whole extra mass, but only a fraction of it. And then if you increase it further, this fraction will tend to 1. Okay. So I have written these things up here in a statement. Okay, let me just, so that's really, so this is law of large numbers. Let me just say what happens at the point of the transition. You can explicitly compute a probability P such that you see either everything in the maximum or everything homogeneously distributed. There's nothing in between ever happening, right? And this P is explicit, but depends on lower order terms here in how much mass you throw into the system. So you have to subtract the critical scale. Okay. And the scale I wrote here, so it's square root of L log L for the power law case. And for the stretch exponentials case, this is exactly the same statement. Again, it's like L to the 1 over 1 plus gamma. Okay. Let me not say anything more about this. Rather mention one more, say, extension of this kind of work. So before I do that, sorry, so this is a law of large numbers. We also have statements about CLT, like so fluctuation behavior, which I don't mention here, but these are also in that paper. To come to something like the metastability, let me just mention this. I hope I'm doing okay. Okay, good. So yes, so let me come back to this. So this is again this function, phi as a function of the density. So this is blue part and this is this red part that we have seen before, right? Okay, so now you can actually, if you really do the simulation, you have a system of size L and you throw in n particles, then you are in a canonical situation. We have fixed the number of particles, and there's basically a recursion relation that allows you to compute this normalization factor explicitly in a numeric way, right, a recursive way. And then you can compute the current under the canonical distribution, the expected current, also by using this recursion. So numerically you can do this to any kind of system size, and you see that actually these things, so these curves, should converge to this curve and then to the flattened part. That's what they do, but they do it in a very peculiar way, right? And you see that they actually develop a little jump here, and this jump is exactly reminiscent of the jump we have seen before, in fact, if you zoom into the critical point, this condensate appears suddenly rather than a continuous way, right? So that's still what you can see here. And so what we have done here is basically we want to investigate what happens to this little jump here in an appropriate scaling limit. So we recenter our plot here at the critical point, and we blow up the two axes, and we hope that we get a data collapse for these curves when we scale them correctly. That's what happens here. So this is basically the critical point, and we inflate the axis by a certain scale, which is related to the one I showed you before in the theorem. So we add in, we have L times rho C particles plus some extra stuff, which we write as delta rho times a small parameter, which is chosen correctly. And then you see that this curve here, or this part of the curve, has a scaling limit that looks like this, which the black curve that we know explicit, but I don't write it here. Okay, good. So that's this thing. And then what are these dashed lines? Now this is now the metastability. So you can even establish the existence of some local minima. I'll explain that in a second outside here. So this is a metastable branch of this curve, and this is a stable one, right? So what do I mean with that? So if I now fix an excess mass of my system, and I look along this line, so what is the probability of seeing? So I'm looking at the probability that the maximum takes a certain value, right? So I'm telling you that the typical value is related to this part of the curve or this part of the curve, and there's another value which is metastable, is related to these two branches. So how you can quantify that is basically just looking at this probability and show that it has a large deviation rate function on a certain scale, and this has a double well structure. And this is what we have done here. So this is actually this large deviation rate function plotted in a particular variable that is not so important, but now it has a double well structure corresponding to the condensed phase here and the fluid version here, and these are these two metastable lines here, right? And then, of course, the idea is that if you want your system to go from here to here, you have to pass this potential barrier. Okay, and of course, this is not should not be the end of the story. So this is a stationary evidence so that you have some kind of metastability here. But of course, what we are working on basically right now is that we would try to establish this in a dynamic set, that we can actually show that there is in a certain scaling limit a process that jumps between these two values, the Markovian process. So that's the idea of this thing. Okay, thank you.
Question? Otherwise, we think again.
Thank you. So I'd like to thank, first of all, the organizers for organizing this wonderful school. It's been a pleasure to be here. So what I'd like to tell you about today is invasion percolation on regular trees. So let me tell you, first of all, what the definition is. Then I'll tell you briefly about the structure and structural representation that we have for it. And finally, what I'll try and do is tell you about its scaling limit. So this is the scaling limit of a certain kind of tree. And so we'll be representing it in terms of paths. And I'll tell you how to do that, how to piece together pieces of the tree, and maybe more if I have time. If you were here at the beginning of the school for Jean-François Legault's lectures, you will have heard a lot about representing trees by contour functions, and this will be sort of similar. I should mention also that this work is joint work with Omer Angel, Frank Den Hollander, Gordon Slade, and also Mathieu Merle. Okay, so first of all, the definition. So what I'm going to do is look at an infinite graph, let's say finite degrees, and select some sort of origin. And I'm going to primarily be concerned with the regular tree case. So and I'm going to assign each edge some sort of uniform weight. Now I'm going to grow a cluster dynamically according to the following deterministic rule with these random weights. I start with the origin and I look at the boundary of my cluster and add the smallest weight edge. And then I repeat with my larger cluster. So I'm going some sort of percolation type connected subgraph inductively. And I'm going to look at the infinite union of all those after infinitely many steps. So here's an example. The blue dot is my origin. I've got the boundary is those three green edges. I invade the smallest edge, which is 0.1. Next, the next smallest is 0.65, 0.7, 0.15, and so on. Okay, so eventually you leave this area of the graph and you would carry on. So I'm going to end up with some infinite connected graph. And this is closely related, as its name would rather suggest, to ordinary percolation, where you just define edges to be open or closed independently. So for example, if I look at all the edges whose weight is below p, that would be a model of ordinary percolation with parameter p. And I could talk about things like whether a vertex is connected to infinity at level p by edges of weight at most p, and so on. And I'll skip this edge out. Now, one thing I'll definitely need from percolation is the idea of the critical parameter. So I look at the percolation probability, which is the probability that you have an infinite cluster from a fixed point, the origin. And this is an increasing function of p by monotonicity. And so there's a critical threshold PC at which you start to be positive. And it's well known that for most sort of non-trivial graphs, this PC is strictly between 0 and 1, and it represents a phase transition. Okay. Another relation to percolation is the following theorem. So if I look at the weights that I invade as a sequence of numbers, the weights that I invade in my invasion process, then with probability 1 on a wide class of graphs, they tend towards PC. And so this means that invasion percolation is what's called an example of self-organized criticality. It finds this critical value PC, which before I had to define by a sort of piecing together of a function probability defined defined in a somewhat roundabout way. This PC. Here I can just find it as an almost sure limit from my dynamic model. Okay. In fact, we'll see that they tend towards PC. As k goes to infinity. So as you look higher up the tree, you're getting subcritical parameters, but they're increasingly close to criticality. And in fact, we can get scaling kinds of estimates. If you look at PC minus WK, that's approximately of order 1 over k. And we'll actually be more explicit later about the exact size of that. Okay, so that's the equation we have here. And indeed, I'm going to, I could describe the Markov process dynamics, but I'll skip that. Now, when we do a scaling analysis of this process, which is necessary to understand the structure of these subcritical clusters that are branching off, what we get is the following result. Having rescaled by k and done a certain amount of manipulation with sigmas and so on, we find that the limit of this process, pc minus wk hat, scales toward a process that we call L of t, the lower envelope, the Poisson lower envelope process. I'll just draw you the picture because the picture is sort of fun to draw. In the first quadrant, you draw a Poisson point process and then track the running minimum of the points you've seen in your process. So I see this point, and eventually I jump down to a lower point, and I run until I find the next lower point below that, and so on. And who knows what it did up there. Okay, the point is actually not so much for our purposes here to know about this process exactly, but just to say that it's a nice process that we can control extremely well. We can, for example, get its multivariate Laplace transform and this kind of thing. Okay, and once you put all these results together, you can get a lot of specific scaling information. So, for example, if you want to know about the number of vertices that are ultimately invaded at distance n from the origin, so here I had a couple from here plus the backbone, and we might have had another branch up here that contributed. That scales as n. The number of vertices at height n is of order n as well. And in fact, we can even get a lovely expression for the Laplace transform of that limiting variable. Okay, so this is a long enough equation that you shouldn't try and write it down. In any case, we get some expression for the Laplace transform. And as you can see, it's pretty nasty. It's not something you'd really want to have to deal with extensively. Okay, so time permitting, towards the end, I'll actually give a more compact and probabilistic description of what this limit of the rescaled limit of Cn actually is. Okay. I'm going backwards, okay? Okay, so let me pass to the tree issue. And I want to describe how I'm going to represent paths, trees by paths, and then some issues about how you piece together trees when you've got infinite objects. No? Okay, so earlier we heard about contour functions, and now I'm going to tell you about Lukasiewicz paths. So for a finite tree, say this one, I can associate to it its contour function, which is where you just trace along and record your height as you go along. This is actually not really the best function for our purposes, because that function is not typically will be difficult to describe for our types of trees. It's actually more relevant to consider the Lukasiewicz path, because it will be a Markov process. And there's a relatively simple relation between the two, which I won't describe here, but in any case, as I say, we'll consider Lukasiewicz paths. So how do those work? I'm going to start my path at 0, and I'm going to order the vertices of my tree in planar order. So this is, I think, depth first search order. Now what I'm going to do is explore the tree in this order, and at each stage I'm going to take an increment in my walk, which is the number of children minus 1. So here I had 2 children, so I go up by 1. Here I had no children, so I go down by 1. Here I had 3 children, so I go up by 2. And the next 3 vertices all have no children, so I go down by 1 each time. And when I come to the last vertex, I've run out of vertices, and I'm going to be at -1. Okay, and for the context that we're considering, where we have this where we are essentially looking at Galton-Watson trees, you can convince yourself that this will be actually a random walk, where the step distribution is not quite the usual random walk distribution, but some other one related to the offspring size. Okay, and just as we saw results for rescaling of the contour functions earlier, there are also results for Galton-Watson trees. And we'd like to apply those in our case, where we have Galton-Watson trees with varying parameters. So there are a couple of issues that I'll try and tell you how to address. Well, I guess there are actually three issues. One is that these WKs actually vary. The parameters of our percolation process vary. That's not important at all. Now, what is slightly more relevant is that the invasion cluster is not a finite tree, such as that one, but an infinite tree with an infinite backbone. And the other issue is that, and that it's slightly subtle actually, is that the vertices on the backbone, well, evidently if you're this vertex here on the backbone, one of your edges is used up by being the next edge in the backbone. So actually the off-backbone branches I'm considering have one less child or potential child than normal. And this, well, there are ways around it which are slightly complicated, but in any case you end up with various factors involving sigma minus 1 and sigma. Okay. So what I do want to describe is this first point, though. If we have an infinite backbone, what are you going to do with the trees? Okay, so you have two main sort of options. One is that suppose I had this tree, and then I had one more, which was perhaps that one. How would you encode them by some sort of path? So the first thing you could do, and apparently I should have drawn them closer together. So the first thing you could do would be to create an artificial edge between them so that you did have a finite tree, and then deal with the Lukasiewicz path of that tree. Now, what would that mean? That would mean that you would actually have modified your heights a bit. It would have meant that you would be a bit higher here, and you would not have gone down below 0 at the end of the first tree, and then you would have carried on with the second tree. And so, roughly speaking, this corresponds to a sort of reflection process. And it's actually not the one I'm going to want to do. So the other thing I could do is no longer require my path to stay positive. I could just start my next Lukasiewicz path from -1 and carry on. So now if I do that, well, my second tree is going to start here. And, well, so I have two steps. So I go up 1, down 1, down 1, and down another one. So I'd end up, after finishing the second tree, I would have gone down to -2. Okay. And in fact, you can convince yourself that the infimum process counts the number of trees you've encoded. As I mentioned, the first path, the first option of these two corresponds to reflecting, which is not always so convenient. And the second approach is going to lead to what I call y of t in the next slides. And let me just observe that if you were just in a Galton-Watson type context, this is just a regular random walk, because you walk for a while, you go down, and, well, you just carry on, you just walk some more. So this is sort of the unperturbed version, and the reflected one is in a way more complicated. Okay, so I get we end up with the following result. I'm going to express my sorry, I'm going to deal with a couple of issues here. Now, when I drew this picture here, I drew the backbone sort of in the middle. And when you start thinking about encoding trees, if I go up along the left, it's going to take a while before I get to the right. So I'm going to actually assume for the moment that my backbone was all the way on the right. When you do that, you get, well, let me abbreviate in the interest of time by saying that this is not quite the right thing to do. Particularly, what you get is this funny 2y minus 3y bar, minus the infimum process. And this is sort of a funny object. We couldn't really understand what this behaves like. Y bar is the solution to a certain ODE, SDE, which we can explain. What's actually much better to do is to leave the backbone where it was. So let's just say that there is part of the tree is on the left, we forget about the tree on the right, and describe only half of it at a time. Okay. What happens when you do that is that if you look at the, for example, if you look at the contour function, it means that you had to take your original process width, which went down. You had to correct a bit by subtracting, by adding 1 for each tree. That was subtracting one y bar sub t. And then if you want to get your contour function, you actually have to go up, because as you go up the backbone, you get higher up. So that means you've subtracted yt bar under bar a second time, and that corresponds to adding your the counting process of trees twice to recover your contour function. Okay. One other issue that I'll mention is that there's another sort of strange reason why this is the right thing to do. So suppose that, forget about the yt, which I didn't really even describe to you, and suppose that yt was actually just a Brownian motion. So if you did that, if you did this process, y minus y bar, that means you're subtracting the infimum of a Brownian motion. And that exactly means that you're actually reflecting it. You're reflecting it at 0 to get a reflected Brownian motion. If you now subtract y bar a second time, so that you've raised it even higher, what that means is you've added well, that means that you're, sorry. That means that you've actually produced a Bessel-free process. And that's as if you had taken a Brownian motion, told it never to hit 0, and taken the result. Okay, sorry for the time. Thank you.
Quick question. Otherwise, we thank you.
Eu não sei como funciona esse filme. Pode prender? Pode.
Thank you for
Não sei se vai agarrar porque
session. It's my pleasure to
balançar muito.
present our next speaker, Daniel Valesin from Escola de Polytechnic de Goodman, and he'll be talking multitype contact process, extinction.
Okay, so I'm very happy for the opportunity to speak at this great school, and I would like to thank the organizers for it. So part of what I'm going to say is a joint work with Henrique Angel, Leandro Pimentel, and my PhD advisor, Tom Mumford. So I'll talk about some problems in the contact process. I'll start with talking a bit about the contact process in general. So the contact process is a class of interacting particle systems that was introduced in 1974 by Harris, and it's usually taken as a model for the spread of an infection in a biological population. So it can be defined in any locally finite graph, but here I'll consider it in Z, in Z, which is the setting for all the problems that I'll consider. So the interpretation is that each site of Z is an individual, and individuals can be either healthy or infected. Healthy is 0, infected is 1. So the state space is 0, 1 to the power of Z. And the dynamics will have two parameters, lambda larger than 0 and m an integer, infection rate and infection range. And the dynamics works in the following way. So healthy individuals do nothing, they just wait. And infected individuals, they wait an exponential time of parameter 1, after which they get healthy. But additionally, they wait an exponential time of parameter lambda, after which they choose someone to transmit the infection. And this choice is made uniformly in the m neighbors to the right and m neighbors to the left, where m is the range of the process. So as most of you probably know, this process can be constructed with a graphical construction or Harris construction, which is simply a family of Poisson processes. So we have a set of for each site we have a process dxt, which is the healings, and these are drawn as x's. So here time is growing upwards. We have z here, the individuals. And for each site we plot the axis as the healings. And also for each pair xy at distance less than m, less than or equal to m, we have a Poisson process of parameter lambda over 2m, which is drawn as arrows. And so this gives this set of arrivals of Poisson processes, x's and arrows. This is called the Harris construction. And if we also have the initial configuration of the system, we can determine the state of the system at a given time t. So this is done here. Black, of course, black is infected and white is healthy. And we draw these vertical paths which cannot cross the axis because the axes are healings, but are allowed to traverse the arrows. And this allows us to determine who's healthy and who's infected at time t. So one obvious fact about this dynamics is that the state where everyone is healthy is absorbing. So once we reach it, we stay there forever because the infection doesn't simply appear from nowhere. But also another fact that I want to say is we have phase transition for the contact process. So we take the initial configuration where only the origin is infected, and if we fix the range and we change the rate lambda, there exists a lambda critical, a value such that if lambda is less than or equal to lambda critical, the infection disappears eventually with probability 1. Otherwise, if lambda is strictly larger than lambda critical, there is a positive chance that for all positive times you have someone infected. So, okay, that's all I want to say about one-type contact process. And we want to consider versions of this dynamics with more than one type of occupant. So we have to change the interpretation a little bit, and now to think that each site in Z is a region of space, which can be either empty or occupied by some biological species. So as before, the occupant may die, and as before, the occupant may send descendants to another region. And so to specify such a model, we have to say which are the types, of course, which are the rates of death, of transmission, which are the ranges. But most importantly, we have to say what happens when one type tries to invade a region that is already taken by another type. And these choices give rise to completely different models. And we will study two of them. One of them is called grass bushes trees, and the other is the multi-type contact process. So for grass bushes trees, I'll take here two species, blues and reds, which are 1s and 2s. And they both have the same death rates, 1 as before, the same ranges, M1 and M2 equal, and the same infection rates, lambdas, which are taken supercritical. So up to here, everything is symmetric. The only difference will be that the blues are allowed to displace the reds, to invade the regions taken by the reds, but not the converse. The reds may not displace the blues. So this model was studied by Durrett and Moller and Durrett and Swindle, and it's called grass bushes trees because empty sites are considered to have grass, and blues are trees and reds are bushes. So the trees can displace bushes, but bushes cannot displace trees. And, so this is so here's a picture of the dynamics with the initial configuration where to the left of the origin we have trees and to the right of the origin we have bushes. And I want to point out some facts about this. First, that it may be constructed with a Harris construction exactly as before, because the rates and the ranges are all the same. Second, if we stop distinguishing blues and reds, we get the original contact process. But another nice property of this particular process is that from the point of view of the blues, the reds and the whites are indistinguishable. So we can think of the evolution as something that is done in two steps. We can first let the blues evolve, and then the region that is not corroded by the blues give a random environment for the reds to evolve. So this is a very useful, very nice property of this model. And I'll ask you to notice that up there we have a region a mixed region, an intermediate region, which is composed of blues and reds. And this is only possible when the range of the process is strictly larger than 1. That is, when we have no nearest neighbor interaction. We are allowed to transmit, or to jump over individual regions and transmit far away. Otherwise, we don't have this mixed region, which we call interface. And so, formally, we would define this as interface process. We take the initial configuration that I mentioned. We define the rightmost blue, the leftmost red, and IT denotes the size of the interface at time t. So, of course, if we're in this situation down here, IT will be negative, because here we don't have an interface. We have just an empty region delimited by the last blue and the first red. But as I said, if we have a positive range of the a range that is strictly larger than 1, we might be in this first situation, where we do have an interface. And so we might wonder if this interface eventually gets large. And how it behaves. And Cox and Durrett in '95 conjectured that this is a stochastically tight process. And why do we care? Why do they care about this process, and why did they make this conjecture? Well, they made this conjecture in a paper about the voter model. They were trying to make to make a model for a phenomenon in ecology, where you have an animal species that exists. We have 2 types of animal species that exist in a certain country, but they occupy homogeneous regions, and the transition from one region to the other is given by a sharp, a small a region of coexistence, but they don't mixture themselves. They don't. They stay confined to their regions. So they were trying to give a model that exhibited this behavior, and so we proved this conjecture. I will not say anything about our methods, just that we strongly relied on the fact that I described that the dynamics can be thought of as a 2-step dynamics. First the blues, then the reds. Okay, enough about grass, bushes, trees. Now about the multi-type contact process. Again, we have 2 types, blues and reds. Again, they have both equal death rates, equal ranges, and equal supercritical infection rates. But now it's completely symmetric. So no one is allowed to displace anyone else. The blues cannot displace the reds cannot displace the blues. So this model was introduced by Claudia Neuhauser in 1992. And so some properties again. We have that nice property that if we look at the black and white process, we see the original contact process with 1 type of occupant. But now as I said, we are in a completely symmetric situation, and we don't have that nice property that we had before, that we are allowed to ignore one of the species and study the evolution of the other. We are indeed forced to consider the interaction in some way. And so here's a picture of the process, and so here I take exactly the same initial configuration, and I ask exactly the same question. We have an interface, is it tight? So we have proven this conjecture, but also sorry, it was not a conjecture, but we proved this. I guess it was my conjecture, but another question seemed interesting for this model, which is, for which initial configurations can we be sure that the blues will become extinct? So this is not very clear from the intuitive point of view. In this configuration, it's more or less clear that that guy in the middle there has no hope of making it, of having an infinite descendancy. But if we change this one a little bit and start putting the reds very sparsely, then it more or less, we might wonder if the blues can put up a fight here and have an infinite descendancy. And also in this situation, it's not clear, where we have infinitely many reds in that direction, but we have a block of blues and then everything empty. So we might wonder if the blues and reds here will have an interface where they will fight, but the blues that are free to that direction can run away and have an infinite descendancy. So here's a theorem. The blues almost surely disappear if and only if A, they appear in finite number, and B, they are surrounded by infinitely many reds on both sides. So to answer the question, in the first two configurations, the blues will almost surely disappear, and in the third one, they have a positive probability of surviving. So thank you. Maybe some facts about stationary distributions are known, but about trajectory properties of the process itself, very little is known. For example, in dimension 2, if you take everything empty and one blue and one red, we don't know if there is a positive probability that they both exist.
Any other question? Otherwise, we thank Danielle and all the speakers and all the audience.